Okay, now we're left with a puzzle though, and that is having to do with the weather. But hot air rises. How can hot air rise if nature wants to make things with mass fall from high places to low places? Well, in order to understand that, let's first make a real simple contraption. Let's make a little contraption with two pulleys. Okay, these are two wheels that can turn around, and I'm going to imagine hanging two objects from it. This is a string which is going around the pulleys. And let's suppose I start with one which is 5 kilograms and one which is 2 kilograms. Two different weights, okay? They're connected by these pulleys. They can smoothly ride up and down on the pulleys. The pulleys might have some friction in them, that's okay, doesn't matter. And let's just say that there's a table here. So this is where our starting point is. Now, what happens? What does nature like to do with this? Well, you all know that it's going to cause the 5 kilogram one to go down and the 2 kilogram one to go up. All right. So already this seems like a violation of our principle before, which was that massive objects are supposed to fall. Here's a massive object which is not falling, but it's going up. Well, let's take a look at the total energy here and see if we can figure out what the story is. So here's our initial situation. So our initial energy, I'm going to just call that UI, initial energy is, first of all, we need to say what the height is. So let's just pick a convenient number like 0.5 meters. Okay? So let's say our initial height is 0.5 meters. The mass of this one is 5 kilograms. So the energy of this mass here must be mgh. So that's 5 kilograms times 0.5 meters times little g. Now, the height of this one is 0. So I know that if I look at my equation here for energy, the height is 0, so there must be no energy in this one. Okay, so don't even have to write this down. So the initial energy is simply UI times 5 kilograms times 0.5 meters times little g, so that would be 4.9 times 5, which is about 24.5 joules. Okay, now let's look at the final situation. These things are going to move, so I will just move them here. At the end, after nature has caused this one to fall down and this one to rise up, if this string is good string and doesn't stretch, then it'll be the same length as it was before, and that means that the height here will be, again, 0.5 meters. Okay, but now the energy is different. So here's our final energy, final. It's going to be all in this weight. This one has a height of 0. So once again, if the height is 0, then it'll have no energy. So this one has all the potential energy. And I'm going to say that is 2 kilograms times 0.5 meters times little g. 2 times 0.5 is 1 times little g, which is 9.8. So that would be 9.8 joules. Well, this is kind of nice. Now we can actually draw an energy diagram to show what this process, how this process really works. So let's do that. Okay, just to remind you, so this is the process we're talking about, where we have a 5 kilogram weight here and the 2 kilogram weight here, and they're tied around to pulleys, and then they switch places. So the 5 kilogram weight falls and the 2 kilogram weight is raised up. Now, how do I draw an energy diagram for this? Well, what am I going to put in here? Let's put this, the pulleys are sort of what do the trick here. So let's put in, like we did before, the heavy mass. So this will be the 5 kilograms, and it starts out at a high position, and when we come out, it's still, at the end, it's still 5 kilograms, but this time the height is 0. So the energy is carried in here, and there's no energy carried back out there. So here's our energy carried in. 25 joules, or approximately 25 joules. What happens to the other weight here? Well, the other weight started out with 0 energy, and at the end it had some positive energy. So the other weight is carrying some of the energy that this weight had at the beginning. So we can draw that in this way. Here's my 2 kilogram weight coming in. Here it has no height, and here it has 0.5 meters. So here h is 0, here h is 0.5 meters, here the height is 0.5 meters, here the height is 0. It's still 2 kilograms when it comes out. Here, though, the energy it's carrying is less than 25 joules. So the difference between the energy we started with for this smaller weight and the energy that we ended with this larger weight is 9.8 joules. But 25 joules and 9.8 joules are not the same. So if I start with 25 joules and I end up with 9.8 joules, something must have happened to the rest of the energy. Well, for the case of this example, there's no other place that no other energy carrier that I can see in this problem except for entropy. When in doubt, it's probably being carried away by entropy. In this case, the entropy is carrying away by a couple of different ways. One is that the pulleys might have a little friction, might even have a lot of friction, so they're sort of squeak, 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 as the string is pulled around the pulleys, and might heat up the pulleys a little bit. Also, when the 5 kilogram weight slams into the table, it might cause an impact and might put a little bit of heat into the weight and a little bit of heat into the table every time two things bang together. There's always some entropy created. Notice this is an irreversible process too. You won't see this thing, you won't see these weights suddenly switch positions. You'll never see this film run backwards. So that's another indication that entropy must be created. So entropy is created, and the entropy that is created must be carrying away the remaining energy. So that is about 15 joules carried away by entropy. So this thing is kind of an interesting situation. If you have energy coming from somewhere else, you can raise something from a low height up to a high height. But that energy has got to come from somewhere. In this case, you can take gravitational energy. If you have a lot of gravitational energy here and a little bit you can get some of that, transfer some of that into gravitational energy for something else. But you're always going to get some entropy created in the process. So in order to lift things up, for example, the warm air in the atmosphere, there has to be a constant input of energy because entropy is always being created in the process. So we could say about this that to raise a mass, so masses, I said, generally naturally tend to fall. But to raise a mass, another source of energy is required. So in this case, in order to raise this mass from a low height up to a high height, it's sort of going backwards against what nature wants to do with it. Well, in order to do that, we're going to need a source of energy. And in this case, the source of energy comes from this other weight, which started up high and fell down low.